from my point of view, I feel that I have taken G's theory further and finished it off.
Welcome to the Measure podcast. Today I'm speaking with Geoff Lyman. Geoff is the author of the book Theory and Practice of Particulate Sampling, and he has written more than 50 papers on sampling. In this conversation we have a discussion, a whole range of topics. We're talking about the sampling theory, we're talking about what's happening out there, what people are writing and what they're discovering, about running heterogeneity tests, building sampling equipment. We're talking about the gold industry, the coal industry, and particularly we're talking about some controversies. Do we still need to have some of these conversations? And particularly we cover topics such as, why is it so difficult to explain to people why sampling is important? How can we demonstrate that we are saving money if we invest in good sampling? Anyway, I hope you enjoyed the conversation. Let's get into it. Hey Geoff, how's it going?
Pretty good, René. How are you? I hope you aren't freezing to death the way I am.
No, we've got the heat pump on full tilt here, so it was a wee bit chilly in the morning, but we got there. So all good. I'm still clamping my notebook, and my fingers are a wee bit cold, but hopefully the brain is still on, so should be okay.
That's good. That's good.
Hey, good to see you in good spirits, man. Look, it's been good to talk, and maybe we'll start with a bit of background on your professional career. And you've got quite an interesting background. I'd love to hear a bit more about how you sailed into the sampling space. And for those who don't know you, and the work that you've done, take us on a bit of a journey.
Well, I started life as a chemical engineer at McGill, and having decided that I didn't want to go and work in the States, I decided to switch to metallurgical engineering and did a master's degree on froth flotation, surface chemistry. And then I got an invitation to come to Australia to the JK Mineral Research Centre, and got into doing all sorts of research there, developing nuclear sensing instruments and so on. So background in nuclear physics I had to acquire. And then when I started doing a lot of plant work, I discovered that I better learn something about sampling, because no one in the mineral industry, when they quoted a recovery or some kind of performance figure for a piece of equipment, they never put error bars on it, which I thought was cheating. Because, as one guy once said, if I had $1 million for every 1% extra recovery that people have promised me, I'd be a billionaire. And people would say, oh yes, well, we increased the recovery by 2%, but was that a significant difference or was it not? So I decided that getting into sampling and understanding the uncertainties associated with one's samples from which one calculated the recoveries would be a good thing. And so basically that's how I got into sampling, and I bought Pierre G's book and went to Francis Pitard's course, and then began doing things for myself. And I think it was 1985 that I published my first paper on sampling, and I've been doing so ever since. And I now have probably 50, 60 publications on sampling, and as you have on your desk, I have an attempt at generating a textbook that really tells the whole story, both mathematically and practically. So that's sort of where I am, and I've sampled everything from hamburger to diamonds.
Yeah, that's the first one might be a bit tricky, but that's a pretty awesome background. And I'm interested if you then get into this sampling, right, and you do the course, and you said you bought Pierre G's book. What were you thinking when you first started reading this stuff? I'm just interested, from somebody coming outside of the mining industry, picking up that book, looking at the problems. What's the sort of thought process that went through your head over the years, or as you started getting into this? What were you thinking when you picked up that material?
Well, I was looking for answers. I wanted to know how to sample properly, and I wanted to know how to put error bars on my results. And frankly, Pierre G's book didn't really give that to me. And I found the notation that he uses in his book, I found that pretty turgid. I really had trouble trying to cut through what he was doing. And if truth be told, it took me years to digest his book. And my first paper on the subject was an attempt to actually use a different approach, such as I've used in my textbook, to make the whole thing a little bit less difficult for people to learn. And indeed, I think that, people who pick up G's book or Pitard's book, which is very similar to G's, I think they have a very hard time plowing through it.
So why is that then? Because, you'd say you wanted to make it easier, but it sounds to me that, or it feels to me, reading through parts of the book and through some of your papers, you've got a very strong mathematical angle to all of this. Are the solutions presented by G necessarily not that mathematical, or are they? Why is it breaking down? And for a lot of people, it will be the opposite, right? The more mathematical you make it, for particular people in the mining industry, it won't make it easier; it makes it harder. So, what can you just break that down when you say easier?
Yeah,
absolutely. Now, what G did was, he got a concept of heterogeneity of particles with respect to the lot. He got that concept in his mind. And he said, okay, it's a difference in, it's a relative difference in assay weighted by a particle mass factor. And if you look at his most fundamental equations, that's exactly what you find when he goes to calculate what he calls the IH, the intrinsic heterogeneity, or whatever he calls it, IH anyway. Now, his arguments were entirely heuristic. They were not mathematical. Me, being a chemical engineer who had oceans of mathematics rammed down his throat and couldn't survive without mastering these oceans of mathematics, I thought, well, there's got to be a better way. So I said to myself, well, what's the fundamental issue behind sampling? And I decided that the most fundamental issue behind sampling is that the number of particles of any one type that fall into a particular size fraction follows a Poisson distribution. And if you start from that premise and you write down the composition of a sample as a function of the assays that you have at hand and the mass fractions in the various size fractions, if you write that down and then you use simple propagation of variance, where you assume that the variance derives from the Poisson distribution, you end up with G's formula for the fundamental sampling error. And you can do this in one A4 page. You do not need 8 to 10 chapters to do it. And I thought, wow, this should, for anybody who can follow a simple propagation of variance formula, which is pretty damn common, this should make it a lot easier for people. And everything in my book is based on this premise of Poisson distribution of particle numbers.
So if that's the case, sorry to interrupt, but it almost sounds like the problem has been solved, right? Let's stop talking, right? And right now, or last week, we both missed the sampling conference organized every couple of years, and this time in Norway. What are we talking about those conferences then, if the problem's been solved? And is there any uptake in this, or is the lack of uptake perhaps simply ascribed to the fact that none of us know our maths well enough? I mean, why is it not everybody saying, look, we've solved this, thanks Geoff, and let's move on?
Well, let me just make one remark, and that is that the last thing that I did before I wrote the book was that I managed to calculate the entire sampling distribution. That is, the probability density function that your samples will follow if you sample in a mechanically correct manner. Now, G, in his derivations, he never got past estimating a variance. And of course, that's only the second moment of a distribution. If you want to know everything there is to know about a given statistic, and the sample assay is a simple statistic, you need to know the probability density function. So from my point of view, I feel that I have taken G's theory further and finished it off. The problem, of course, is that the method is very mathematical. And I don't expect a lot of people to be able to follow the mathematics. But be that as it may, getting back to what you've just asked, why do we continue to have sampling conferences? Well, that's because the industry does it badly. And one of G's greatest contribution to sampling, and for this we should be eternally grateful, was that he looked carefully at the entire sampling process and said, okay, where can we foul up? Where can we mess up in our sampling? Well, he describes all sorts of different errors. First of all, there's the sample delimitation error. Then there's an extraction error. And then there are various, we've got grouping and segregation errors. We've got all these mysterious 3-letter acronyms for the 10 different kinds of sampling error you can commit. But, if we could just get people sampling in a mechanically correct manner, if we could pound that into people's heads, that you must use a proper cross-stream cutter or something that behaves in an equivalent manner, and then you must preserve the integrity of your sample, and you must do everything in the best possible manner. That is to say, don't use a fixed riffle. Use a rotary sample divider. Right down until you extract your analytical aliquot. And I do have clients that do that. There are miniature sample dividers that will do the trick. If we could get everybody doing that, a lot of the sampling problems that people suffer and a lot of the unexplained variances that people suffer from would disappear. That, to me, is the most critical aspect, mechanically correct sampling from go to woe.
Yeah, look, that's great, but I go to these sites and try to help people out with their sampling problems. And a question that I always run into is okay, demonstrate to me the value that we're either adding or cost that we're saving by changing from this to that. And the whole problem with that is everybody knows that sampling is important, but to actually put on a piece of paper why or to what extent that rotary splitter on the benchtop at the lab gives you better variance, and how much better variance, and how much is enough or not enough, for what purpose, that part of the solution is missing. And it's very hard, in my experience, to express that for people, right? And there are papers, and I remember Francis himself talks about, this $1 billion loss at this copper, project in Chile or something, just to give the thing.
That was the work he did with Pedro Carrasco.
Exactly, yeah, and that's obviously what we all sense we need, because the moment we can express it in dollars, we can tell people, hey, this stuff costs you money. And that's all well and good, and a lot of technical managers that I run into at these mines, they get that principle, but still, if you tell them they need a different sampling system that costs them $50,000, if it's a rotary bench splitter doesn't cost as much, but or a splitter on a rig, or maybe a proper sampler at the plant, right, for the feed. I mean, that's not 50 grand, you're talking about a couple $1 million there, right? If you want to do that properly, because, they have a scraper and it comes off the belt and that's a sampler, right? So tell me why that investment of a couple $1 million makes all the difference. And putting the tests in place to demonstrate that very thing, that's difficult, because you can't predict the future. You can't predict how much variance you're going to be saving or how much more accurate you're going to be. What I don't know, solutions do we have in place to deal with that? Because that's really what you want to demonstrate. The moment you can do that, we can move on, because everybody knows that we need to do better sampling. But the quantification of that, I find that a bit mysterious. Have you got some thoughts there?
Well, my favorite example, I spent 19 years working with the coal industry here in Australia. And they went through a big change in terms of what they did from the point of view of sampling. And basically they were running dense medium and flotation plants, and when they were selling coking coal, they usually had a target of 10% ash. But they could only determine their ash content of what they were shipping to the port to plus or minus, say, 0.2% ash. And that meant that they had to put coal out of the plant at 9.7%. Now, you can make the argument and you can say, right, if you can cut your standard deviation in half, instead of putting coal out of the plant at 9.7, you can put it out at 9.85. And when you work out how many extra tons that gets you out of your coal deposit, the sampling system, the most gold-plated sampling system, is paid for in a month or two. Even if you go to some of the really classy sampling systems that are sold by the folks who are in the business, I guess we shouldn't name them, but that is the most compelling argument. And it's not difficult for people, if they would do a variographic experiment, they would be able to determine what their sampling error is, but they won't do it. Even if they've got a crummy sampler, they could do a variographic experiment, and if you take the intercept of the variogram at 0, that's your error, or that's your variance. And if they would just do this, they would realize that, oh my God, there is money to be made here by sailing closer to our specification. And this means not just ash or copper content, it means moisture as well. Man, it's really good business to sell people water.
Mm-hmm. Yeah, that's a good point. But maybe I like what Francis, and I think it was him where I first read it anyway. There's probably, and obviously, instances before that, but he really drilled down on the DQO, right, the data quality objective. And with RSC, we've woven that into every bit of work that we do, because without an objective, you don't know what you're skating towards, and it's also very difficult to play that quantification game. And everybody has heard of fit for purpose, but we don't really fully understand what we're doing with it, right? So to me, fit for purpose and DQO. And that's perhaps a bit easier if you've got materials with specification. I mean, coal is a good example because, in cement, and I think Francis has a couple of good examples on cement specification, then it becomes easy because indeed you use your chronostatistics, you get your variogram intercept, and that's your variance, and then you can play with that. You can put that on your control charts, and it's either above it and it's bad, and it's within it, it's good. I mean, we're now sort of digressing into process control a little bit, but the principle is the same. You need a data quality objective, and you need to sort of quantify that quality, right? Because, and you and I talked about this before, and that's a bit of a quest for me, obviously, quantifying quality, because quality is such a loose concept. And if we're talking about better or worse, right, performance of variance or accuracy, we need to have language to enable to define what is better or worse, and therefore we need to quantify it. Right, you see where I'm going? So the quantification of what is good accuracy and what is bad precision, for instance, becomes a real focus then, because if a variance of 22%, and we can have a 50 minutes segue on what that really means, obviously, as you and I have been discussing, but if you would agree to some sort of construct for that quantification, then we can start benchmarking perhaps what is good and bad. And to give you a classic example, we know, quote unquote, that analytical variance, and I'm using quotation marks because even that term itself is obviously wrought with issues. How do you find the actual analytical variance if you're talking about a classic fire assay for gold? But be that as it may, if you would accept that is 2 to 4%, then you have a target, you have a number, and if it's not 4%, if it's 6%, then that's not good, and you're quote unquote losing money or whatever it may be. How can we get the industry moving in that space of quantification, or am I really just taking it in a place where there is no exits here and we will forever be on this road? Do you see solutions in that space that once we understand the sampling theory, now we can break it down mechanically, mathematically? Can we now get to a point where we have an even playing field and what we understand data quality to be, and can we quantify that?
Well, I think, you used the word fit for purpose. And people bandy about that seriously overused word representative. Well, representative, what does that mean? It really should mean fit for purpose. Now, we take samples for process control. We can probably tolerate a higher or a lesser precision on those than we can for commercial sampling.
Exactly.
So we need people to sit down. We need the financial people in the industry to sit down and decide, okay, let's do a sensitivity analysis of what better precision would actually, what advantage that would give us. Can we sail closer to a specification? Can we get paid more? Can we avoid penalties? That's one way of attacking this problem. On the other hand, apart from the financial side of things, I think that the way we get people to understand what good precision is first of all, we teach them how to measure it properly.
Yeah, exactly.
And I think that some of your concepts that you've got, that you want to get material onto the web via a website that provides tutorial material to people, I think that, and with really nice practical examples that aren't too complex, that people can work through and see the advantage of in a reasonable space of time before their minds go numb. If we can achieve that, if we can get a site going that teaches that sort of thing, rather than people having to read Pierre G's book or Francis's book or Kim's book or whatever, if we can get that going where young metallurgists, young geologists can go and see this stuff in action and begin to appreciate really how simple it is, how simple the rules are to get good results, I think that would be an enormous step forward. As far as I know, there ain't no such thing on the web at this point in time. And that needs to get going. I think
we're working on it.
I know. I just had an email from a colleague in Brazil, and she's done a huge amount of work on ore heterogeneity. She has graduate students that could be used as slave labor to do all sorts of sample analyses and so on. And she didn't go to Norway, and she expressed disappointment in the sampling community that is represented in Norway. And that, I think, is driven by the fact that whatever's being taught, it isn't getting across. We need to get these simple ideas of fit for purpose, simple examples of how you can make more money with more precise sampling. We need a place where we can get this across to the young folks without drowning them in mathematics.
Yeah, sure. Now, look, that's an excellent message. And, at risk of saying something controversial, is that Norway setting and this general grouping that goes to these conferences, are we an echo chamber? And do we need those outside influences to look at this from a different way? I mean, the PRG medal seems to go around, in circles, but how many more people are deserving of the PRG medal? And, what message are we sending with it? Is everybody allowed these conferences and everybody allowed to speak? Is it turning into an echo chamber, and are we spinning the same stuff around without ever coming out of the rabbit hole? I might leave that as a hanging question, and we might circle back to that, Geoff. But look, you mentioned heterogeneity studies, and I made a note here. I've run a few of these, and I remember ringing Dick Minnitt up after, a few of them, and I said, Dick, you put that brilliant paper out that makes it super simple for dummies like me to just literally walk through the steps and do exactly what you're supposed to be doing, and you get these answers. And in his paper, sorry, I just the actual year and the title escapes me, but you get your 4 beautiful lines on your LN plot, and you regress it, and fantastic, you're away. I got very poor results out of that, and not once or twice, but several times. And you are charging your client for this heterogeneity study that the industry will have you do to solve all the mysteries, right? But as we all know, the study itself is based on the sample, the very bulk sample that you select to run the study, and then there is all these actual grouping and segregation errors that you actually introduce if you don't pay attention for a couple of seconds. And the whole study becomes quite difficult. Long introduction story to get to the question: should we keep doing these heterogeneity tests? And is one person's heterogeneity test, is Bonger and Sons better than Francis' test and all the other stuff? And I don't actually know what we're doing at the moment at the sort of top end of the industry, what the settled agreement is on what test is best. But is there any use in that, or with the work that you've done, that becomes obsolete if you can get particular information from the sampling distribution, from the particle distribution? What do we need these tests? Just maybe clarify that.
Well, I took some of Dick's early data. He did a test where he crushed, and he did it with Connie Spangenberg from Anglo Gold, and the 2 papers that came out of that, those guys both used the same ore, and their results lay right on top of each other. So that's 2 sets of experimental work that, my God, they agreed, my God. And they agreed extraordinarily well. And I took those data, and the good thing about that data is that what they did was, instead of doing heterogeneity tests on individual size fractions, they crushed an ore to 4 different top sizes. And they then took subsamples of the whole sampling distribution. Say they crushed it to 25 mil. They subsampled the whole minus 25 and took that down into 32 subsamples and did screen fire assay to extinction on 280 grams of sample. And they did the same thing at 12 millimeters and some other different sizes. And that test worked, I think, extremely well because, first of all, by avoiding separating into size fractions, you avoid some extra preparation errors. And second of all, you get a number that is relevant for your ore if you crushed it to 25 millimeters or you crushed it to 12 millimeters. You get, from the 32 assays that you get a distribution of results. And it's the variance of that distribution that tells you what your sampling error actually is. I went a step further, and this was a gold ore, and I back calculated what size distribution of gold particles would result in such outcomes. And lo and behold, the top size, the 95% passing size, the apparent 95% passing size of my gold grains in the sample, which, I could calculate the sampling distribution by using my magic characteristic function method. I got the top size of my gold reducing as the top size of this ore was broken. And what was happening was the gold clusters that had an effective size that was quite large, those clusters were being broken up. So the gold was actually liberating in some respect. The gold particles weren't breaking, but the size distribution of the gold was changing because I was breaking clusters. And, for that particular ore, the work that these guys did told the full story about that ore. And it was 12 grams per ton. And now a lot of people don't have 12 grams per ton. I'd love to. It'd be nice, yeah. But, you know, that's, to me, that's the kind of test that you need to do. And you don't need to plot up the results. You can just use your variances and use that to design your sampling protocol, because it's the sample preparation that is most important.
Well, we'll put so we'll put a link in the description to that paper. But you know, obviously you would have communicated with Dick on this. Have you guys sort of cross-referenced the work that you've done with his data, and are you guys on the same page there, or?
When I gave my PRG oration, as they call it, in Beijing in 2019, Dick was in the audience, and he acknowledged that he and Connie had in fact used the same ore. You know, he was right there. So we have in that respect communicated that there was a different way of looking at his material. And this K-alpha model, I don't think PRG ever intended it to be used the way it is used. In my book and in some of my papers, I show that this K-alpha model doesn't really do the trick.
Right.
You're better off just looking at variance, or IH, as a function of the top size to which you crush your material. And
It's interesting.
if you can get, I sent a sample for a client, a Canadian client that I dealt with recently. I sent the material off to a lab to have a heterogeneity test done of the type that I've just described.
Yeah.
And we won't mention any names, but the commercial laboratory screwed it up. They didn't have the right gear to do the work, and they weren't committed, you know.
It's extremely important that no variance and no errors get introduced, because that's the whole point of the entire process. If people carrying out the test at every level are not 100% on board what you're trying to do, then the whole thing might be a complete waste of time. Even one sample, right, or one action anywhere in that entire chain could screw the whole thing up. So there's definitely some good advice in that. Geoff will take that on board. But it's interesting. So what I'm hearing you say is, you know, heterogeneity studies definitely have their place still if you do it right, and if you know what you're doing. So that's really good feedback. And but you know, the whole K-alpha thing, I hear you there.
And you've got to select your sample properly in the first place.
Yeah.
You don't want to get a heterogeneity of an uncommon part of one of your lesser domains in your mind. You want to know what the heterogeneity is of the ores that are making money for you.
Yeah. Don't pick something that is slightly below your cutoff grade, because it's unlikely to be doing you any good.
Exactly, it's not relevant. No.
Yeah. Now look, that's I hear you there. Just maybe stepping sideways briefly. I mean, you and I also talked about, you know, simulations, and in terms of building the right sampling equipment. You know, simulating and modeling with the various software packages to work out what the material was doing in a cone splitter, for instance. And there are all these advanced modeling packages on the market now that's supposed to do that. But you mentioned to me, look, you know, it all sounds great, but there's so many conditions that you need to set up and things to be aware of. Could you just take us through your thoughts on, you know, is this something that in the next 5 or 10 years is going to be the way to model our ore running through a splitter to see what variance we're going to get, and whether that instrument or mechanical device that we're building is doing the job, or what do you think?
Well, you know, I designed what I thought was the world's greatest hammer sampler, or cross-belt sampler, and it has this really neat mathematical shape that's supposed to make sure that it doesn't knock the wrong material off the belt. And that's all well and good. But the problem with cross-belt samplers is actually cleaning the belt. You don't want particles rolling under the back edge of the cross-belt sampler. And if you push the head against the belt hard enough, you need, for most ores, you need 75 to 100 kilowatt motor drive on the damn sampler.
Wow. Yeah.
You need a vast amount of power. In fact, there was a paper in Norway, and they used a 65 kilowatt servo motor to drive the head. And now they describe it as the biggest one in the world, but I don't think it was quite as big as the one I built for Asmang. But, 75, 80, 90 kilowatt drive on a motor is huge. But if you're going to get a clean sample off the belt with a cross belt sampler, that's the sort of thing you need to do. I have clients around the world that use cross belt samplers and they don't clean the belt. And the head does not move at constant speed. And this is a problem, particularly with cross belt samplers. Now, getting back to your point, can we simulate this? No.
Mm-hmm. No.
The rolling of particles underneath the back of the head of a cross belt sampler, it is so difficult to do. To get it right is almost impossible. You're much better off to take high-speed video of your actual sampler. And, I did this for a client in WA that had a very, very large tonnage of damp material, kind of soggy stuff, sticky, ugly, dreadful to sample material coming up their belt. And I took high-speed video for them. And boom.
Yeah. So does that mean that, I'm quite the fan of proper stop belt sampling. If you're there to watch it and to guide it, make sure that delineation is good, that you don't have any IDEs, delimitation, extraction areas and all the rest of it. They'll be quite functional because you can obviously scale it up and down, get some good chronostatistics and get some good background data. Are you a fan of those, or have you used those?
Yep, I have, and it's very hard work to do. It ends up being expensive, both for the plant, because you need a lot of samples, René, and to get them to start and stop that belt. Most belts will only take a certain number of starts and stops with a loaded belt per hour. Otherwise, you're going to bugger your motors. But if you watch what you're doing and you take a big enough sample off the belt, and then treat that sample properly, you will get good samples. It's the only way to get a correct sample off a belt. Because with a mechanical sampler, again, unless you're taking high-speed video and watching very, very carefully, you don't know whether it's mechanically correct or not. And if it's not mechanically correct, you're wasting your time and money.
Well, maybe following on from that one, I mean, we started at the start talking about the bench top rotary sample divider at the lab, and let's talk about the classic gold sample. You said you've been able to implement that. I've worked at one mine where they had one, but they stopped using it because it was extra work, and this is a fairly sizable mine, and they know what they're doing. I mean, a lot of things were going very well there, but the delay there that caused at that point in time, it was better for them to go through the scooping process of the pulp out of the ring mill and get the 200 grams in a bag that way. And you quite often hear yourself talking to the lab manager, and they said, no, there is hardly any difference in variance, and where the data come from, I don't know at that point in time. Question, have you been able to quantify that difference, or do you just know that these rotary samples improve? I mean, what arguments have you used there? Because this is a recurring one. Every lab audit that you ever do in a gold mine, you'll have that discussion. And I feel, going back to our favorite fit for purpose again, that, on the entire variance, story from front to back, from what they do, collecting the sample to crushing and prepping and all the rest of it, what happens right at the back end, arguably not the biggest difference that it makes. Can you just clarify for us, quote unquote, once and for all, what your views are there?
Well, I'm obviously sampling with a scoop is a mechanically incorrect manner of sampling. So, if your packet of dirt has been sitting in the back of a truck coming from the mine to the lab, the gold is all at the bottom of the packet, whichever way it was oriented in the truck. And when the analyst takes that envelope full of dirt and does a little shake, mixing it, and then takes a scoop off the top, well, for ores that segregate where you've got not enough pulverization, or you've got liberated heavy components like gold grains in there, that's an obvious problem. Now, the evidence for the value of rotary sample division against fixed riffles or scooping, there is some very old data that is publicly available. There is very little that is new. And really, what one needs to do in this day and age is go to someone who has a difficult ore, take a little miniature rotary sample divider with you, and get them to do the tests, and 30 odd samples will tell the tale. And I just think that we need somehow, maybe we need a government research grant or something to look into this. In Australia it would be the Australian Research Council. You probably have a similar outfit in New Zealand. The Canadians could use Sterk. Someone really needs to do this and get that data into the public domain. No one really wants to know because scooping a sample is so easy. Now, when I was building equipment in South Africa, Anglo Platinum was one of my really big clients. And I built a thing called a variable split sample divider. And their problem was taking concentrates that had been sampled from trucks as a damp or wet filter cake. It was dried. It turned into a relatively hard, clumpy mass. They broke that down, and then originally they did various rotary sample division, but they ended up scooping. And I built them these rotary or these variable split sample dividers so that they could take a pulverized or mashed up sample of this dried concentrate of any mass whatsoever, put it in the machine, and get exactly 150 or 200 grams out. Sampling in a mechanically correct manner, taking hundreds of increments as that material was fed past the cutter. They actually went from having 6 or 8 guys on 3 shifts preparing these samples. When they got the machines, they went to having 4 guys on 1.5 shifts. That saved them a vast amount of money, and their variances went down. So,
There's your argument.
It doesn't have to be difficult. And, if people are moaning about the time it takes to split out the analytical aliquot, buy 6 miniature rotary sample dividers and put samples in one after another. And by the time you finish setting up number 6, number 1 is finished, and you haven't wasted any time at all.
Yeah. They're not that expensive in the end.
No, you can buy them for 10 grand.
Yeah. Now, look, hopefully that will get the discussion picking up a little bit there. But good thoughts there. I'm a fan, but definitely see the arguments at the labs quite often, and there's the lab managers, and there's obviously pressure, particularly in the fire assay space, right? Everything, the bottom line is under pressure all of the time, and every mini increment of seconds somewhere makes an impact on turnaround time, and that's obviously key to bottlenecks. And so so it's always good to sit here as the theorists and the geologists coming in and shooting from the hip and taking photos of prep stations and saying you need to get this, you need to get that. But there's obviously a pragmatic component to that as well that I try to be aware of. But I think on balance, there is a solution there that gives the client a better a better or higher quality sample, and it doesn't have to impact the actual production time. and you know, the extra cost. If you've got a large operation, you know, $10,000 for one of those machines isn't going to break the budget. So there is a big benefit in that equation there. But now look, let's leave that there. That's good thoughts. Hey, before we close off here, what do you consider, you know, the major area? What would you work on now to look for change yourself? I mean, the book is out, so this is obviously your life's work, and I recommend everybody to go pick up a copy. Full disclosure, we actually sell your book through the website, so just as a, you know, facilitation more than anything. So people interested in the book can find it through a link on our website. But you know, where would you go from here with sampling? I mean, you're obviously doing your consulting. What big major solutions are to be found here? What papers are to be written here? I mean, you and I are working on a paper at the moment, obviously, but beyond that, what would you suggest is still out there for people to crack?
Well, I think that we understand sampling theory. I don't think there's anything more to be said about sampling theory, about the mathematics or the statistics or whatever you want to call it. That's finished. We also understand what mechanically correct sampling is. You know, we avoid the fundamental boo-boos in extraction and delimitation. The next thing we need to do to get people doing the right thing is education.
Sure. Yeah.
And you know, people might not want to read my book. They might not want to read the mathematical parts. They can read the non-mathematical parts by skipping over the math. That's fine. And I think there's some good advice in there. I sing the song about mechanically correct sampling pretty loud. And you know, people should do that. And to get people doing that, and to get away from this scooping of samples and messing up their analytical aliquots and increasing their analytical variance, and maybe even biasing it. And that's the terrible thing, is bias. Eh? And you can't, as Francis quite rightly says, the bias today is different from the bias tomorrow. It's a chameleon. It's an ever-changing target. So bias tests are usually a waste of time and money. But if we can get people doing things properly, correctly, and I think the only way we're going to do that is through proper education, that's where the industry needs to go. We need to have the big mining houses educating their people properly. And I would also say, when plants are designed, don't let the accountants cut out the sampling equipment. The sampling equipment is extremely important. And to get the capital cost of that plant down, many times the sampling equipment is removed, and even worse, the plant is built in such a way that retrofitting proper samplers is almost impossible.
It's impossible. Yeah.
That is a terrible crime. And the mining industry or the mineral processing industry has to recognize that. And, you know, those are big ticket items. You're talking $10, $20 million that you can save by making it impossible to put sampling equipment in. But it'll cost you $50 million to retrofit it.
Yeah, no, I completely agree with that, and I see that all the time. And you know, the message is loud and clear. If you don't have any data, if you can't measure it, and you don't know what your system is doing, you're losing money somewhere. I mean, I think that's a pretty clear message. But maybe going all the way back, because like you joked at the start, you also work in the hamburger industry. But you know, on a more serious note, you obviously work across industries, right? Every time I look at these kind of problems, I can't help but think, surely somebody has solved all of this in a different industry. And we know that in mining, we're sometimes a bit conservative with particularly these kind of solutions. You know, you and I discussed as well in geostatistics, you know, we're still using inverse distance and ordinary kriging 60, 70 years old. And there's nothing wrong with that in principle. But, you know, are we just indeed, going back to the echo chamber comment again, is this all been solved in the medicine industry or in the food industry or whatever? I mean, surely they have industries to the same size and where the same dollars are involved. Is this the same problem over there?
Unfortunately, yes. The pharmaceutical industry is beginning to get smarter, and they're beginning to realize that they have to sample correctly if they're going to make sure that none of the pills that they're producing are going to cause someone to overdose or not get the correct dose of the medication. I did quite a bit of work with the Canadian Grain Commission some years ago, and I looked carefully at the equipment that was being sold into the grain industry. And there is a company in the United States, who shall remain nameless, who are selling mechanically incorrect samplers into the industry. And the industry doesn't seem to give a damn. They don't know. They don't know. Now, it's an education problem yet again, René. And by and large, I don't think that there are many industries, if any, that do it 100% right from go to whoa.
Yeah. Well, that's good to know, and maybe that's a good point to move on. But yeah, really interesting. I mean, obviously, talking about sampling, I can do it all day long, and as I'm sure you can. But I think we'll probably start to bore people brainless. So, if anybody has any interest in what we've discussed or any particular items, I'm sure we'll find some comments one way or the other. Again, the book is a good start, and there is actually a video of you presenting some parts of your book online that I'll put in the description as well, because you came over to New Zealand and did a little road show. That was really nice, and those videos, or there's one video online for people if they're interested. But yeah, thanks so much for coming on and sharing your thoughts. It's been really good, and we should do it again.
Well, whenever you're ready, I'm always ready to proselytize, and bang my tambourine.
Yeah, well, maybe we'll bring a couple other people on the show as well, because it's always good to have some discussion between other people, different opinions, and thinking what they say, and could be a good discussion. It's the very thing at conferences that should happen more, instead of us listening to a paper on some case study of somebody picking up some samples, everybody clapping after 20 minutes on the spot. Sorry, no time for questions, moving on to the next speaker. Perhaps we should have some more open debates where we actually really challenge each other in some of these points. I mean, what's wrong in this formula? What is wrong in this approach? Or actually, wow, that thing that you come up with is fantastic. Maybe that sort of dialogue is a way to get out of this. I'm not sure that this channel is necessarily the solution to everything, but like you said, education and dialogue, and it's not coming out in the sampling space, and hopefully this will be a little kickstart. So yeah, excited to see where we can take it.
Yeah, well, I would applaud that, René, and as I say, I'm always ready to bang my tambourine and debate with all comers. All my colleagues in the industry, I'm prepared to take any single one of them, or any of them in a group on. I don't think that they fundamentally have different views from mine. They all have troubles getting clients to do the right thing. They know what the right thing is. And, education, and it's got to be simplified. Yeah,
exactly. Well, that's where hopefully I can help, because if I keep joking to you, if I understand it, then hopefully, I can try and explain it as well, because the maths, I think I have a reasonable understanding of the maths, but obviously not to the tune that you do, and as probably is needed here. So if I can help translate the message somehow, and reach out to an audience of geologists that might not have gotten into geology before because of their strengths in maths, I think that would be a bridge that I'd love to help cross. And maybe you can play the tambourine, and I'll add more cowbell, and together we'll all come out fine. So
yeah. I think that would be a great idea, René, and thanks very much for asking me to contribute.
No, fantastic. Hey, very good to see you, and hope to chat soon again.